what it is mathematically. It's the root mean squared deviation of the height from its mean value. So basically, the greater the roughness, the greater that the interface width will be. But the key point, which is different from what is usually done, is that the length scale over which it is calculated is changed. So what does that mean? If you look at a sort of cartoon of a rough surface here, if I now look on a small length scale, you will see that the interface width is actually really quite small. If I look on a larger length scale, it's larger. So what scaling analysis does is it presents in an easy form this information about how the roughness depends on the length scale. Now, very often, what the data will look like is something like this. And you can see that what's happening is that for small length scales, the interface width is small, and it increases as you increase the length scale. It doesn't increase indefinitely, because if you are going to have this increasing indefinitely, well, pretty obviously the roughness would gradually get bigger than the universe. And we know that that is not a reasonable thing to assume. So at some point, the roughness saturates. So that saturation roughness, or saturation interface width, is called WSAT. Another thing which is very important is the length scale at which this crossover takes place. Because when you make a calculation of W as a function of L and get a plot like this, then what you very often will find is that it has this shape, and this crossover length is really characteristic because that is a measure of the feature size. So that what actually happens is that the behavior mathematically, this is a straight line very often. If it's a straight line on a log-log graph, what that means is it's saying that the interface width is going as a power law with the length scale. And this H actually has a particular name. It's called the Hurst exponent. For a surface which is consisting of just grains that are not fractal-like, H is usually very close to 1 when you do the calculation. And I've already said that W of L will be equal to the saturation value above the crossover length. And this is actually showing some real experimental data. And what you can see is that as you increase the thickness, you see that this position of this knee, the crossover length, is moving gradually towards the right. The crossover length is moving roughly where I'm indicating here. Larger thickness is higher crossover length. That means that the feature size is bigger. So that is an observation. I'm a physicist. I would like to know a little why that could happen. So what causes surface coarsening? Well, one way is if this is a very simple schematic that goes back to the 1960s, and it indicates a way in which competition could lead to coarsening. Look at this grain B. In a very simple model, which assumes that all of the facets grow at the same rate, you can see that this facet, because of the angle it is at, it will grow like that. This one will grow like this. This one will grow like that. But because of the angles, eventually this B is going to be buried. So that's one possible way in which a surface can become coarser. But it's not the only one. And if you want to actually see whether it really is taking place, then it's quite useful to do some sort of an experiment. So now I'm going to say something about high-speed atomic force microscopy. High-speed atomic force microscopy is a really, really cool technique. Unfortunately, like many really cool techniques, it's extremely expensive. So when I moved to Pakistan, I had to say goodbye to my access to the high-speed atomic force microscope, at least on the short term. I have to do now what most of you do, which is that if you want access to the really cool technology, you have to collaborate. So what I do is I just continue to collaborate with people back in Bristol. But why is it cool? Because it has got subatomic height resolution. And that's, of course, what any atomic force microscope has. But what it has in addition is that it can, instead of you sit there and twiddle your thumbs for half an hour while you're getting an image 20 microns by 20 microns, you can do it within seconds. And that is really impressive. So this has been used at electric deposition before. It was used to study the early stages of deposition on single crystals. But what we did for the first time that was new is that we looked at the later stages of growth and polycrystalline films, trying to answer that question, what gives rise to surface coarsening? So this is the instrument. And the reason why I was able to do this in Bristol is that the instrument is actually a spin out of the University of Bristol, a company called Bristol Nanodynamics. Now, what is neat about the instrument, it's not the actual standard AFM part, which is really quite normal. It's a contact mode cantilever, detector, and laser, like in so many atomic force microscopes. What is really important is the stage on which the sample is mounted, because that stage can move super fast and still keep the tip in contact and keep everything working properly. And that's what gives you the opportunity to get data with incredibly high speed. So the experiment that we did is we actually looked at deposition on a microelectrode, patterned using UV photolithography. Why would we use a microelectrode? Well, the reason for that is actually what I talked about in my first talk. You remember I said that when you do electric deposition and some other techniques, mass transport can give rise to instabilities. And if you have a really dilute electrolyte like we have here, and if you are trying to look at deposition on a small area in a dilute electrolyte, the best way of doing that is to make sure that you have got good mass transport. And that's what we have here, because if you have a microelectrode, then you have got your counter electrode very much bigger than where you're depositing. So the lines of current come together, and that means you have got good mass transport, and you do not have to worry about depleting the electrolyte, which you would if you had a large area electrode. So that's the system. So these are just experimental details. Notice the speed. The speed is 2 frames per second. What I'll do now is I'll show you a video of the surface actually growing. You can tell that this data is not perfect because you can see that a particular triangle size shape is appearing. That triangular shape is something you should always watch for if you do atomic force microscopy, because what it tells you is that you are actually partly imaging your tip. So this data has a convolution of features from the tip and features from the actual surface. But the surface coarsening phenomenon that you see is real. So now let's have a look at it and see how this very quite fine-grained structure becomes rough. And this video is speeded up, but it's not speeded up by so much. The whole experiment only takes 1 or 2 minutes. So you can see that gradually getting coarser and coarser and coarser. So if you look at that, you see the surface coarsening taking place in real time. And that's actually the first time, as far as I know, that that has ever been seen. And for somebody who studies surface coarsening, to be able to see it as it happens is really rather nice. So let's look at some of this in detail. What's the evidence for the surface coarsening? Well, I'll just show you again a few frames from that video, one after the other. So that is frame 75, 165, pretty clearly more coarse, and 275, much coarser. If you look in more detail, you can then get an idea about how it actually gets coarser. So the first thing to point out is that you do actually see the effect of the surface coarsening in the scaling data. Remember I said that you very often see this shape of a straight line down here, gradient close to 1, and then approach to saturation up here. So this is logarithm of the surface width, logarithm of the length scale. If you want to know how to do scaling analysis, it's very easy to find that from the literature, and it's very easy to implement in Python or another program, which is basically how I do it. So what you can see here is, here too, there is actually some evidence that there is a movement from here more towards here. There is, in the scaling data, evidence of the coarsening. There is also a power law behavior of how that crossover depends with time. Power laws are really fun because they appear in so many places, and you can argue that this is a sign of any sort of system where length scale is independent, but actually working out where the power law comes from and why it is there is a very interesting challenge for many physics of complexity problems. So to find out how fast the film grows, we actually looked at the edge of one of these samples. The edge is where you go from here, this is actually the resist, to here, which is where the actual film is. And if you look at that at different times, it is pretty rough. But you can see that in the initial frame, this red line is showing that this is the base of the electrode, and all the features above this are coming from the deposition. So if you average over an area, you can work out what the growth rate actually is. Now a little bit to look at the details of the growth. Here we've got two grains, which, because I'm a very original person, I call X and Y. And the interesting thing is to look at those grains and see what happens as the film gets thicker. And what's really surprising is that one grain grows so much faster than the other one. I'll go back again. Initially, X is actually bigger and higher than Y is. But after only a few frames, Y suddenly becomes bigger. And I call this accelerated local growth. And that was really unexpected when we saw that. The Van der Drift model that I showed you earlier doesn't say anything about coarsening taking place in this sort of way. And you can see this if you take a cross-section of the image. Those are the two grains, X and Y. Look at what happens to them. Y overtakes X really fast. So what that is saying is that accelerated local growth, you can't ignore that if you want to understand how a film gets coarser. So the next sort of thing to do is sort of look conceptually at how accelerated local growth could make the film structure coarser. And that's what I'm doing in these cartoons. This is a really simple schematic of a polycrystalline film. I'm just representing the surface by this sawtooth. If I could get that in reality, I would use it for a solar cell. Of course, it's in reality a little bit more complex. So imagine that I've got accelerated local growth. Here, what I'm saying is that this grain and this grain grows faster than the others in such a way that it actually overgrows. So that's an example of accelerated local growth with overgrowth. And how is that coarser? Because the feature size here is clearly bigger than the feature size there. You also could imagine that accelerated local growth could make a film structure coarser even without overgrowth. So what you can see here is I've again selected two grains, and I've said they grow faster than the others, but without actually growing over the others. You might say this doesn't make the structure coarser. Well, actually it does make it coarser, because now the sort of feature size, the length scale between comparable features is still much bigger here than it is here. So you could get surface coarsening as a result of accelerated local growth with overgrowth or without. So here is an example where we can see grain overgrowth. We've got two grains, 1 and 2. Now look at what happens. If you look at the later frame, here's the previous one, 1 and 2. You can see now 1 has completely overtaken 2. So that's showing you that overgrowth really does take place. And that's one of the reasons for coarsening. Now let's look again at the grain which I showed you before. That's X and Y. And now I'm looking at what the slope is. Because if you have got the increase in coarsening as a result of one grain becoming sharper, then what that of course means is that the slope increases. So is that actually observed? Certainly it is, because you can see here is what the previous slope was. Here's what the new one is. So the slope has definitely increased. And in fact, if you use the atomic force microscopy images to calculate what the local slope is, you can actually see that although the peak does not change very much here, as you make the film thicker and thicker, you get many more areas where the slope is larger. And again, for those of you who do atomic force microscopy, I strongly recommend doing this analysis of the local slope. It's incredibly easy. A simple Python program is enough to achieve it. And you actually will see things that are meaningful and interesting. So, of course, we then can ask what could actually cause the accelerated local growth. What's really interesting is that it's not something that is taking place uniformly. It's not that we have all these grains and this one always grows faster than this one. What we actually see is that suddenly one grain starts to grow. And another thing is, you remember I showed you two grains, X and Y. If it was actually the mass transport that was responsible for the accelerated local growth, then we would have actually expected X to grow faster than Y, because X is bigger than Y, and therefore the mass transport is faster. So it could also be a microstructural issue, a greater density of the half crystal sites. Those are the ones which, if you remember from my previous talk, those are the ones where metal atoms are incorporated in a film, or if not metal atoms, atoms are of an oxide or semiconductor film. Another thing which can happen is that the film doesn't necessarily stay with the same structure. Once you deposit the material, you can get movement of grain boundaries, you can get movement at the surface. So structural reorganization could also be relevant. However, one thing which almost certainly is going to play a major role is adsorbates. An adsorbate is basically anything that adsorbs to the surface. The additives which we talked about in my previous talk, they are also examples of adsorbates. So here is looking at possibly an effect of adsorption. What this is showing is actually a high-speed atomic force microscope image like the ones we showed before. But what is different here is that you see this sort of corner. Why that corner appears is because during this experiment, we shifted the scan area. So the new scan area is the old scan area, like that. The fact area higher is telling you that where we were doing the deposition before, we were actually growing more rapidly than elsewhere. So that means that the actual scanning is having an effect on the growth. Now, you could argue that if you are scanning a lot, amazingly, my talk continues, so you have no excuse not to listen. My apologies again. So what that's telling you is that the growth is continuing where the scanning is faster than elsewhere. It could be mass transport, because if I'm moving a tip, then I'm actually stirring the electrolyte, and that brings material to the surface. But actually, if that were the case, I would not expect such a sharp boundary. It's actually much more likely that that's just showing the same thing in a cross-section. It's actually much more likely that we see something that was observed previously with standard atomic force microscopy, because it's saying that when you are scanning across the surface, you're actually removing adsorbates. And the adsorbate in this case is, according to the pH was varied. That tells you something about the chemistry of the surface. From those experiments, it became fairly clear that what was being removed was an oxide species. So again, that goes back to what I said previously, that one of the ways that adsorbates affect growth is that they actually block surface sites. But another way that I also mentioned before is they can accelerate growth. So now let's return to scaling analysis. Remember what I showed you before. This is a typical example of a snapshot of a film analyzed looking at the interface width as a function of the length scale. But it's also interesting to see how that changes with time. And very often the changing with time also follows a scaling law, a power law. And what is interesting there is that you have the same sort of W going as L to the power of H with H the Hurst exponent that I showed you before. But now you see time dependence in the saturation roughness. So the saturation roughness increases and increases according to a power law. And this power law coefficient is really an interesting exponent because it tells you something about the whole growth process. So this is what that sort of power law would look like. Here is scaling data as a function of time. And basically, since this is a logarithmic plot and the time dependence is a power law, every time you double the deposition time, you shift the saturation roughness up by the same amount. And because this part remains the same, then automatically the knee has to move to the right. So what that's telling you is if you've got normal scaling, you automatically have got surface coarsening. But it's also possible to have something called anomalous scaling, which means basically the difference is that you have a power law dependence also for small l. So if you look at the actual graphs, the only difference really is that what you see here, that the roughness at the small length scale also increases. And physically, what that's actually telling you is that the slope is increasing as well. So that's what I just pointed out. If you have a non-zero local roughness exponent, in other words, these curves are separate from each other, that the slope is increasing. And you can see the effects of adsorbates very nicely sometimes in scaling data. So what this experiment that I'm going to show you does is it takes a basic underlying copper electrolyte. It's an acid copper electrolyte with the chloric acid added to lower the pH and avoid any problems with oxides. And then what we do is we add a small amount of a particular anion. So first one that we try is we add a little bit of fluoride. That fluoride, being a highly reactive ion, would interact very strongly with the surface. In fact, it does not. And the reason is that fluoride is so chemically reactive that it is coordinated by water from the electrolyte so strongly that it interacts only very weakly with the actual surface. So here we have a little bit of chemistry, and we have a weakly interacting anion, and we see this sort of scaling. And notice here, all of those curves are separate from each other. Remember what I said, that is anomalous scaling. What we can do is we can try different halides. And this is really neat. If you add bromide, which interacts really strongly with the surface, you see that you're going from the situation where you had the anomalous scaling to the normal scaling. So the scaling analysis is telling you that the growth is different. And if you go to normal scaling, what that's telling you is actually also the slope is not changing as much. Scaling analysis is worthwhile doing. Orientation analysis is worthwhile doing. You don't necessarily have to do both, but doing one of the two is often useful. So, as I said, this data shows that anions affect the local slope. And we can show that directly. I said, sometimes you can find slope effects from scaling. Sometimes you can find them by measuring the local slope directly. So we did another experiment, which is looking at nickel electrodeposition. And again, we have an electrolyte which has got a significant addition of chlorite compared to one which doesn't. And this is the PhD work of Aisha Mubshra, who is continuing her PhD in Bristol while I enjoy myself in Pakistan. It's actually really funny because she came from Pakistan to the UK and I went the other way around, but she's still doing a PhD with me. When I told her that I wanted to move to Pakistan, she was a little bit surprised. So here we have the different electrolytes with chloride and no chloride. And you can see, I think, that the pattern looks different. This has got some sort of finger-like structure. This has got much more rounded structure. The challenge with data like this, you can look at it and say this is quite clearly different, but the challenge is to find some sort of way of describing those images quantitatively that is straightforward, that brings out the differences. And actually the slope analysis is one way of doing it. So again, what I plot is I plot the frequency of occurrence of a particular slope, and I'm comparing here, the data is normalized for an 8 micron film and a 4 micron film. And you can see that when there is no chloride, there is actually little change with the thickness of the film. It shifts a little bit to higher angles, but not hugely. On the other hand, when the chloride is present, there's a much greater effect. So this is another illustration of how anions can affect surface slope and therefore the whole growth process of a polycrystalline film. So this is a summary of what I've been saying. Accelerated local growth was a little bit of a surprise when actually looking at the surface coarsening effect in real time. It can involve grain overgrowth. It can involve an increase in slope. Both can lead to structural coarsening. And there are a huge number of open questions. How does microstructure, how does adsorbate really affect the growth? So in the final few minutes, I want to say a little bit about electrodeposited nanostructures. Present is talk. Enables you to make nanostructures in a really straightforward way. Those of you who are already working with titanium nanotubes and with anodic aluminium actually already know the value of electrodeposition and electrochemistry for nanostructure formation. So I'll say a little bit about electrodeposited multilayers. Multilayers that I'm referring to are basically structures consisting of one metal alternating with another. But why they're nanostructures is that the individual layers are really, really thin. And they're of interest for transport measurements. They're of interest because such films could have enhanced corrosion resistance. They can also have enhanced radiation resistance. And this is now quite old data, but it is showing that an electrodeposited multilayer can show giant magnetoresistance resistance. So this is data which is showing how the resistance is changing as a function of the magnetic field. And you can see that there is a magnetoresistance in the van der Pol geometry of 10%, and it takes place over a relatively small field. So this is actually quite a nice magnetotransport behavior. You can make a really inexpensive magnetic field sensor this way. So how would you actually make a metal multilayer? Well, one obvious way would be to have here an electrolyte for one metal, here an electrolyte for another one. I take it, put it in here, put it in here, put it in here, put it in here. That sort of process is difficult. If you are a PhD student and your supervisor asks you, please keep 1,000 times between two different growth systems, because this is Pakistan, you will be polite to your supervisor and say, "Ji haan, sir," or "Madam," depending on the situation. but in reality, this is not a fair thing to ask anybody. You can automate it, but you can also have all of the metals deposited from the same electrolyte. And this is neat, because let's take the example of copper and nickel. Nickel is more reactive, so you have to apply a much more negative potential to deposit nickel than copper. So if I have got copper and nickel in the electrolyte and have a less negative potential, then I'm only going to get copper deposited. In general, at a lower potential, only the most noble metal will be deposited. If I then change the potential to a more negative one, I will get an alloy of the more noble metal and the less noble metal. Now, the neat thing about this is that you can have that alloy consisting mostly of the less noble metal. How? The way that you do that is by making sure that the more noble metal is really dilute. So that means that when you start to deposit all the metals, growth of that metal is limited by diffusion, so you don't get very much of it. You have mostly the less noble metal. So here it is again, most noble, less noble. And so that actually works really very well. And what I also would point out is that you can get materials which are nanostructured in all three dimensions by combining that process which I mentioned with deposition in a template. Template could be something like anodic aluminium oxide, or it could be a polycarbonate membrane in which holes have been etched as ion tracks. But however you have a nanoporous membrane, if you grow the multilayer in it, then you can get nanowires, the kind that we've been hearing about before. But what is different about these nanowires is that they are nanostructured also in the growth direction. And those nanowires, if you look at their magnetotransport properties, because you're looking at magnetotransport with the current flowing perpendicular to the layers, they have a really high magnetoresistance, 50% at room temperature, over 100% at liquid nitrogen temperature. And you can check that you've got really multilayers because you can use X-ray diffraction and you see satellite peaks from a large area multilayer. And if you have got a nanowire, then you can actually see in a transmission electron microscope. I'm not sure if you can see this, but there are actually little lines going across here. And the individual layer thicknesses are only maybe 1 to 2 nanometers. In fact, for the copper-nickel system, you can actually change the deposition so fast that you deposit sub-monolayer quantities of each material and thereby produce a granular alloy. So one very recent result, which I would like to show you, is the problem with a lot of electrodeposition is that you are restricted, if you work with water as your electrolyte, to only those materials that will deposit from water without the water itself breaking down. But you can also use ionic liquids, particularly the inexpensive one, ethylene here, and that actually does give rise to a very nice multilayer structure. So that is the end of my talk. The final part that it was an advertisement, if you like, for the power of electrodeposition in making nanostructures. You can get nanoscale structure in the lab. So thank you very much for listening, and thank you for the whole conference organization.
Well, thank you very much, Professor. I was familiar with this technique, but after hearing the lecture by Professor Walker, I started loving this technique. Well, now we have time for the questions. Please, if you have questions, you are.
Okay, thank you, Professor. Very nice talk. My question is that can we improve the quality of the AFM tip by the coarse motion?
Sorry, say that again.
Can we improve the quality of the tip or the quality of the image by using the coarse in AFM?
By using the fast motion. No, I think if you want to get the very best information on a film which you have grown and is not changing anymore, then you should probably use conventional AFM, because if you scan slowly enough, you can get really, really high resolution over a small area. The advantage, of course, of the high-speed AFM is, firstly, you can look at a much larger area, so that if you have got a film, you can check that what you've looked at is really representative. And the second is, of course, that you can look at growth as it takes place, because you can do in situ atomic force microscopy for electric deposition with a conventional AFM, but you're restricted to a growth rate of a fraction of a monolayer per second, sometimes even per minute. Whereas with the high-speed AFM, you get close to the speeds which are used in commercial electroplating.
Okay, my second question is that in AFM, we have the, usually we obtain the double image through the AFM tip. How can we improve in that situation?
What kind of image? Double image?
Double image.
That is very often a consequence of having a double tip. The only way to improve it is to treat your tips very, very gently. Make sure that your surface is clean and does not have any contamination, because the contamination can cause problems for the tip. Also, if you're doing contact mode, do not make the force of contact too great. Or choose a very high aspect ratio tip, but they are very expensive. But it's all down to the tip. No, it's actually worse, because if you're scanning fast, you have more opportunities to damage the tip, and you will get triangles like I showed you.
Thank you, Professor, for a nice talk on the physics of electrodeposition. That's first time. The question is, what will be the effect of electrolyte concentrations on the structural coarsening?
What is the effect of the electrolyte on the coarsening?
No, the concentration of electrolytes. On
the concentration of the electrolyte. Now, that's a really interesting question. The concentration of the electrolyte will mainly affect the mass transport, but our experiments show that the most important parameter for the metals we look at is actually the deposition potential. So for example, if you want to use a very large negative potential, then you've got a problem, because you will also start to deposit the material very quickly, and you will start to deplete the electrolyte. So you can't apply a very negative potential for a long time. The way of applying it is then to do pulse deposition. So you deposit it for a short time, then you let the solution relax so that the concentration returns, then you deposit again. So the potential is important, because you, through the potential, can change what material is absorbed to the surface. This goes back to a question which was asked in the last lecture. If the absorption is an electrochemical absorption, then potential is key. Potential also affects the movement of the atoms on the surface. You can't say only potential is important. Current is also important, because if you have deposition which is too quick, then you don't get close enough to equilibrium. This is one of the reasons why electrodeposition is both complicated and fun, because you have to worry about all those parameters. Concentration, I would say, is a secondary parameter that you can use to change the current that you have for a particular potential, for example.
Thank you.
Thank you very much, Professor. Nice talk. So I have a question about this overgrowth AFM images. So have you compared these images with other characterization techniques like SEM? Because maybe it is the AFM tip artifacts which you are seeing here.
I don't think that that is, I truly don't think that that is possible. We very often do when we, for example, have anomalous scaling, we do compare our SEM images, focused ion beam images, and that. But in this case, because of the nature of the convolution, it's very hard to see how that could be purely an artifact. But there is an artifact involved in it. We don't have the SEM data for that because we can't get the SEM data in real time, obviously. So you're right, you have to be careful of that. But I am pretty confident that that is correct. However, we're still going back and trying to do more experiments because we only have this set of data that worked really, really well. It's a hard experiment. Now what we want to do is see, does the same thing happen with nickel? So I have the same problem as any Pakistani scientist has, that now my access to the instrument is very restricted, but as soon as I can get access to it, I will try to address problems like you. But we've been doing a huge amount of work to try and remove the tip artifacts. It is hard.
But you can also rotate your samples to see that.
You have to be careful because in many cases you can do that. Rotating the sample will help you, but a lot of people think that rotating the scan direction will help you. It doesn't.
So what is the advantage of high-speed AFM if you are doing?
The advantage of high-speed AFM is that it enables you to look at a, quote, real electrodeposition process. You can look at a process which is taking place on at a growth rate of a fraction of a monolayer per second using conventional AFM. But if you want to understand what I would call real electrodeposition, which is usually growing at tens of nanometers per second, then you have to have some sort of technique which will get the data rapidly. So the advantage is you can look at faster growth. If you're going to grow any film for any application, it has to grow fast.
So have you used the magnetic tips also for AFM measurement?
You could do that, but there wouldn't be any advantage for this system because it's not a magnetic system. If we were looking at some of the multi-layers, it could be interesting. But I think it would be, I don't know that anybody has succeeded in doing magnetic force microscopy at high speed.
Thank you.
Any other questions? Okay. Dr. Lutfan.
Thank you, Professor. I'm actually interested in the slope of the coarsening. Is it the same as it initiates it with the smaller particles? Have you measured the slope of the coarsening?
The slope of the coarsening is something that happens in lots of different systems. And one of the, you can think of different reasons why it could happen. One of them is simply mass transport, that as the grain gets bigger, much deposition may take place on the top of the grain, and it then has to move down towards the grain boundaries. If that process is slow, then the top will grow faster than the rest, and then you will start to see the increase in slope. I think that that is probably one of the main reasons why the slope takes place. And indeed, that would also explain to some extent why additives have the effect they do, because additives will also affect that mass transport. But that is still one of those open questions. You would expect to see some slope because of the sort of Mullins argument of balancing the surface tension with the grain boundary tension, but that wouldn't actually predict an increase in slope.
Any question? Well, if there is no question, let's thank our
Thank you.
speaker.
Thank you.
Recording stopped. Recording in progress. In the name of Allah, most gracious, most merciful. With the permission of Chair, we commence the concluding ceremony of 49th International Nathia Gali Summer College on Physics and Contemporary Needs, beginning with the recitation from the Holy Quran by Muhammad Suhail.
أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم ألم تر كيف فعل ربك بأصحاب الفيل ألم يجعل كيدهم في تضليل وأرسل عليهم طيرا أبابيل ترميهم بحجارة من سجيل فجعلهم كعصف مأكول صدق الله العظيم.
Thank you and Jazakallah Swilsab. Honorable Chief Guest, Dr. Raja Ali Reza Anwar, Hilale Imtiaz, Sitara Imtiaz, Pride of Performance, Chairman, Pakistan Atomic Energy Commission, Member Science, Executive and Scientific Secretaries, distinguished faculty, respected guests, and participants. I would like to extend a warm welcome to all of you as we gather here today for the concluding ceremony of 49th International Nathia Gali Summer College on Physics and Contemporary Needs. Envisioned by Dr. Abdul Salam, Summer College holds a great significance in today's rapidly changing and expanding world of science. The need for collaboration and knowledge sharing has become even more crucial. Ladies and gentlemen, Dr. Shafqat Kareem, Pride of Performance, Scientific Secretary of International Nathia Gali Summer College, plays a key role in bringing together researchers from various fields and providing them with a common platform to accumulate and exchange innovative ideas, latest knowledge, and unique experiences. He will now provide us with a brief overview of the scientific activities of 49th International Nathia Gali Summer College. Sir, please.
Honorable Chairman, Pakistan Atomic Energy Commission, Dr. Raja Ali Reza Anwar, Member Science, Dr. Masood Iqbal, Executive Secretary, and Dr. Manzoor Ikram, foreign faculty, ladies and gentlemen, good morning and assalamu alaikum. I welcome you all in the concluding session of the 49th International Nathia Gali Summer College on Physics and Contemporary Needs. I would like to express my sincere gratitude and appreciation to the Honorable Chairman, Pakistan Atomic Energy Commission, for joining us today despite his demanding schedule. Today, we are going to complete 49 years of scientific discourse without any interruption. This remarkable achievement has been made possible only with the continuous support of Pakistan Atomic Energy Commission. For this, I would like to express my sincere gratitude to the Chairman, Pakistan Atomic Energy Commission, and Dr. Masood Iqbal, the Director of the College, for their enormous support in the organization of this event. In the 49th International Nathia Gali Summer College, we selected 3 emerging technologies for a comprehensive study. The first activity was devoted to the quantum technologies. Quantum technologies represent a cutting-edge field with potential to revolutionize various aspects of our lives, from communication and computing to sensing and security. In this activity, the topics covered include quantum sensing, quantum communication, quantum cryptography, and quantum computing. And in total, 20 lectures were delivered by 8 distinguished faculty members from Texas A&M University, USA, Tsinghua University, China, Chinese Academy of Sciences, China, Zhejiang University, China, Hacettepe University, Turkey, University of Basel, Switzerland, and LUMS, Pakistan. To encourage students, we arranged a poster presentation competition. 50 posters were presented in this activity, and the best 3 were selected by our foreign faculty for certificates and cash prizes. The second activity focused on AI and machine learning technology. These technologies are transforming the way we live, work, and interact with the world today. And these are driving innovation across numerous sectors. During this activity, we have 8 foreign faculty members from 8 different countries who delivered 24 lectures covering the various aspects of artificial intelligence, machine learning, and data science. While 8 posters were presented by students, out of which 2 were selected for the prizes. The last topic of the activity of the college was semiconductor technologies. This is a significant area of research within the field of material science and electronics. And in this activity, the research area covered includes semiconductor devices, semiconductor lasers, energy storage devices, organic semiconductors, quantum dots, 2D material, and electrodeposition techniques. We have 12 lectures delivered by faculty members coming from Chinese Academy of Sciences, China, Yunnan Normal University, China, Institute for Applied Physics, Technical University, Dresden, Cornell University, USA, and LUMS, Pakistan. In this activity last night, we had an excellent session of posters by the students from different universities across the country. 28 students presented top-class work, and the evaluation by the foreign faculty continued late in the night. It was difficult to choose best 3 posters, and their name will be announced shortly. Overall, in the 49th International Nathi Ali Summer College, we received 1,200 applications, and these applications were selected by a technical committee where they selected 80 applicants in each activity with most relevant academic as well as research profile. 80 applicants were selected for in-person participation, while the rest was provided Zoom link, and they remain connected through online. Several universities and research centers remain connected through HEC Edu TV during the activity. Sir, the success of this event is due to our invited faculty members. I am grateful to all the faculty members who have spared their precious time and accepted our invitation to join the summer college and share their knowledge with the participants. I must acknowledge the presence of all the participants who have shown keen interest in the program of the summer college. They were keen to ask pertinent questions during technical session and held extensive discussion with foreign faculty during lectures, tea breaks, and excursion trips. Ladies and gentlemen, an event like this do not happen overnight. The wheels start rolling months ago. I wish to express my sincere thanks to the member of the organizing and the technical committee and the INSC staff who have worked hard day and night to arrange this program to ensure a comfortable stay for you here. This would not have been possible without their dedication and commitments. Our IT team deserves special thanks who made it possible that both in-person and online lectures delivered without any interruption during the 2 weeks. And the transport facilities provided by the Pakistan Atomic Energy Commission and the drivers who work day and night are justified to be acknowledged at this platform. The security personnel who also deserve special thanks to make this event secure and safe. Thanks are also to the retreat hotels for providing us delicious food and taking care of us throughout the summer college. I wish all the faculty members and participants a safe journey back home. Thank you very much, and God bless you.
Thank you, sir. I request Professor Walter Shawar Zakhar, Dean of Engineering and Sciences, LUMS, Pakistan, for his remarks about the 49th International Nathia Summer College.
Thank you very much. I was not expecting to be asked, but to be honest, I should have expected. I really do appreciate all the work that has been put into organizing this summer college. Obviously, I appreciate the invitation given to me, but particularly, I really think that the atmosphere in this college is something exceptional. This college is something which I have not seen anything similar in other countries. It is something which is really valuable for physics, in particular within Pakistan. And I'm really grateful that it is organized by all of the sponsors that we have. The Pakistan Atomic Energy Commission in particular really deserves praise for its foresight in continuing to support this venture. Thank you to all of the people I met and who were so friendly, to all of the students who took it well when I criticized what they had presented. Basically, thanks to everybody participating in this, I wish this whole summer college great success in the future, particularly next year when it will be the Golden Jubilee. Thank you very much, everybody.
Thank you, sir. Now I request Professor Kong Lu, Chinese Academy of Sciences, for his remarks about the 49th International Nathia Summer College.
Okay, thank you. Dear Raj Ali and dear Masood, I'm very glad to give this remarks here, and I'm really enjoy these activities here. And I need to give thanks to the invitation from professors, and I want to thanks to the organization. They provide such a good platform for us to communication, and we have a good experience on the communication and food and hackings. Is a very good memory and an amazing memory for me to hear, and I think this college have very good achievements. I meet some old friends and make new friends here, and I establish cooperation with some professors. We have we are planning to apply projects or do some semiconductor devices in the future. And I found that some students also get the opportunity to find their PhD position or postdoctoral position. This is a good achievement. So I think this is a very successful college, and I hope my lecture and all professors' lecture and the communication will help students to resolve their problems when they face in their research work, and or they can have new idea during this communication, and have a more successful future. And finally, I need to express, and I believe our friendship will last forever, and welcome all of you to China, to Beijing, and communicate more with us. Thank you.
Thank you, sir. Now I request Professor Ting Chu, Chinese Academy of Sciences, for his remarks about the 49th International Nathia Summer College.
Morning, Chairman, and all my Pakistan friends. I'm Dr. Ting Chu, actually from Yunnan Normal University. Actually, this is a really wonderful experience in the past few days. The food is wonderful and the weather is suitable. The most important is Pakistan friends are so kind. I really hope we can have further collaborations in the future in the research work. And I really look forward to my visit to Pakistan next time. Okay, finally, long live for the solid friendship between China and Pakistan. Thank you.
Thank you, sir. I request Chairman Pakistan Atomic Energy Commission and Member Science to give cash prizes and certificates for the poster winners. For the third prize, winner is Wagma Hidayat, Ghulam Isa Khan Institute of Technology. For the second prize, winner is Harunur Rashid, International Islamic University, Islamabad. For the first prize, winner is Mr. Ahmed Usman, Government College University, Lahore. I would now request our worthy chief guest, Chairman Pakistan Atomic Energy Commission, to distribute the souvenirs of the college to the faculty, technical committee, and organizers of International Ethically Summer College. I request Professor Khonglu to please come forward and receive the college shield. Professor Ting Chu. Professor Weiben Chang. Professor Sheng Chen Chu. Professor Walter Schwarzacher. From the technical committee, Dr. Amna Zafar. Dr. Zahid Ali. Dr. Tanveer Ashraf. From the organizing committee, it's myself, Saad Abdullah Makhdoom. Ms. Hina Rashid. Mr. Ahmed Raza. Ms. Amara Naseem. Dr. Mohammad Aslam. Sayyid Fakhr Abbas. Dr. Muhammad Imran. Dr. Rahatullah. Dr. Ishfaq Ahmed. Dr. Shafqat Kareem. Dr. Manzoor Ikram. Member Science, Dr. Masood Iqbal. Yes, sir. Now I request Member Science, Dr. Masood Iqbal, to present Shield of the College to the worthy Chief Guest.
I know the curve is going this way, and next me will be there.
Yes. Thank you, sir.
Otherwise, I'm not thinking that everybody is getting the shield. What should I do?
Thank you, sir. Thank you, sir. Yes, sir. जी सर मैं बुलाऊंगा तो बुला रहे हैं Ladies and gentlemen, Chairman Pakistan Atomic Energy Commission, Dr. Raja Ali Reza Anwar, a recipient of Hilale Imtiaz, Sitara Imtiaz, and Pride Performance, is a strong advocate for the transfer of knowledge and skills for human resource development. He firmly believes in the importance of recognizing and practicing scientific skills to address the diverse range of contemporary needs. I am privileged to invite Chairman Pakistan Atomic Energy Commission for his concluding address. Sir, please.
Bismillahirrahmanirrahim. There are two ways to conclude this. Either I should read this manuscript or I go extempore. I think I prefer to go extempore, and I leave these things. My honorable foreign faculty members, my dear members, secretaries, DGs, organizers, participants, faculty members in the first instance, and then participants, and then वो आपने कहा कि होटल की मैनेजमेंट वो that's very important. वो if it is not going good, तो in the early in the morning वो सुबह से मूड खराब हो जाता है, तो इसका मतलब मूड सारा ठीक रहा है. Let me know where the students are sitting. Please raise their hands. They are about gender balance is not there. Ladies are more than the students. Males, they can raise two hands to balance the. वो हमारे ज़माने में I will be bilingual, Professor, if you must be understanding on account of your relation with Pakistan. I think my Chinese colleagues I am sorry for that if I go bilingual. Uh, so it is very fascinating to be a student of this college. And at the same time, it is much more satisfying to be standing as a chairman before this August hall. I used to be a student like you of this Nathia Gali Summer College back in 1995. I was young at that time, and for the very first time, it was held in PC Bourbon. It was for the first time, and there was a dedicated session of 1 hour on Professor Salam. Professor Salam were alive at that time, but he did not come on account of his ailment. So I was very eager to see that gentleman, a beacon of light, but unfortunately he didn't come. But I was fortunate to take the memories of T.W. Kibble, the particle physicist from Imperial College. They were there, a group along with Professor Salam. And then John Ellis, who is now sitting in CERN with, again, long hair, but an old man. So I took those memories. In the first instance, I tell you from the core of my heart, okay, basically I am a civil engineer and then a nuclear engineer. My bachelor degree is in civil engineering from Engineering University Lahore, and then MS in nuclear engineering from the Center for Nuclear Studies, which is now PIAS, and it was affiliated with Qaeda University at that time back in '88. And then I got PhD from Manchester University in nuclear engineering. Had I not been the engineer, my very first choice was to become a physicist. I liked this field right from the beginning. And now in this age, after having gone through the science, the arts, and everywhere, in religion, every phenomena is run by physical laws. It is nothing, it is everything. Whether my blood is running inside my arteries, it is on account of all these things. Whether my heart is pumping, whether the galaxies are there, whether we are now landing on Mars or looking through the James Webb, which is placed at 1.5 million kilometers. So everything is physics. It's not new that quantum mechanics has arrived now, but it is now the tug war of deterministic approach of Newtonian mechanics, and that of on one side it is Newton and Einstein, and on the other side is standing Bohr. So light is wave or particle, so it is probabilistic. Sometimes it is behaving like that, sometimes, and Einstein never accepts this. He says, no, God doesn't play dice. It is deterministic. If the shields are being given to everybody, and then towards the end, chairman will also get the shield. It's not so that he won't. So I will be bilingual at this stage. As pointed out by Professor, and I was thinking when I was entering into this room that at this stage we are on the 49th Nathia Gali Summer College. Let next time it be the 50th. Organizers, please, and member science, let we start right from the beginning, its preparation, and recall our 50 years. All those who are alive and those who have contributed through this journey for past half century, we honor them next time. Let it be Golden Jubilee, as pointed by Professor very kindly and very rightly. And we should have larger audience, and we should recollect what we kya khoya, kya paya. The very important thing is these colleges were initiated on the basis that we should develop good relations, come together, learn science, then there comes the stage of engineering, and then there comes the stage of technology. Whatsoever you had been learning in quantum mechanics now in these 2 weeks, or artificial intelligence, or computer systems, or semiconductors, blah, 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 it should be transformed towards the end into technology and into the service of mankind for socio-economic development. This is what is desirable. If we are simply playing with our theories and it is of no use to mankind, so it is not good. This particularly I am saying with respect to my scientists, the scientists of my country. They should concentrate first on delivering the tangibles. You should develop those equipment, devices, sensors, blah, blah, systems, which should be having a lot of application for next generation science. The people are sitting from NUST. When I go to NUST, I'm fascinated by many other things. Its location, which is very nice. I was talking to Professor Walter, that it is having a cup-like valley in which it resides. On Srinagar highway, you can't see what is there. But when you enter, it is so nice and so wonderful. I am fascinated. And the second thing I am fascinated is that it carries the poetry of Allama Iqbal. ज़रबे कलीम का वो शेर है, जहाने ताज़ा की अफ़कार ताज़ा से है नमू, कि संगो खश्त से होते नहीं जहां पैदा. Nobody else can understand this as compared to you people. When there was advent of science back in 12th century or 13th century in France, English, England, in German, in Europe, in everywhere, our Mughal Empire was not concentrating on science. They were concentrating on Taj Mahal, blah, blah, blah. कि सिंगो खश्त से होते नहीं जहां पैदा. आप जितनी मर्जी बना लें, जब आप इसको अफकारे ताज़ा नहीं होंगे, it is very. When I look back, when I see myself as a student like you, there is a lot of difference in the society of Pakistan. When I was student like you, there were not any use of computers in our education, 16 years education at bachelor level. In University of Engineering and Technology, Lahore, there used to be one computer center, and it was perhaps 11 IBM old machine, 1130. I know if I don't remember that, but it used to be in one big hall, and then used to be cards. We used to punch the cards, which was perforated at the end like this. वो काटा हुआ होता था इस तरह. Cards थे. Area of circle निकालते थे. We used to write the program for area of circle, pi r square. And very happily, we used to arrange those cards, hand it over to the operator of that, who used to be very harsh on us. Be in a queue. It's very important. You can't enter it. There's AC going on. There's computer. So we used to hand it over. And after 2 days, there was a result. He used to put that in queue and result. And unfortunately, there used to be an error. So to our dismay, so this was the condition when we were students. When I went to Manchester in 1994, there was a lot of difference. Everything was computerized. Everything. The rig which I was using was a gigantic rig, and there used to be 8 or 10 sensors, pressure sensor, temperature sensors, flow meters, blah, blah. And the data was being logged on personal computers. And I was it was totally novice to me. And used to learn besides my problem, which was there under PhD. So you people are very lucky. When I look back, a lot of difference and lot of improvement has occurred in our educational system. Rest assured, as I told on the very first day, and I say it from my core of heart, you are brilliant people. And this is not what I say. I often, in order to improve your esteem, the students which are sitting there, the faculty which is sitting there, I used to quote, when Arfa Karim, our young daughter, who died on account of the cancer, and she was a brilliant brain in IT back in 2012. She was young at that time, 14 or 16. She impressed Bill Gates at that time. And on her death, the European Business Administration Institute quoted that Pakistanis are the 4th intelligent nation across globe. I have worked with many, although few, from here to here, about 10 different nationalities. Well, this is good. This sentence is not bragging. To some extent, it is good. But last time, when the Minister for Planning, Professor Ehsan Iqbal, who is also our senior in UET Lahore, he was studying to inaugurate. When I spelled out these words, so in his speech he said, but I will understand this and accept this when 1/4 of the research papers will be from Pakistan, when 1/4 Nobel laureates will be from Pakistan. So I started thinking about that. And I was reminded of a proverb, which was given by one of our German friends, Professor Walter, one of our Germans. Allah Ta'ala Janasib Kare Professor General Musharraf Saab ko. When he was addressing us on the taking over of Professor Ishfaq and Dr. Dr. Abdul Qadir Khan. He said that I used to study at Staff College, Quetta. At that time, he must be a major or something like that. So German friends were there. A German friend told him, as quoted by General Musharraf, I have seen that you people are brilliant people at individual levels, but you can't work in syndicate. So this is what I add to this 4th brilliant nation across the globe. Unfortunately, I request you to try to learn and work in syndicate. ये नहीं कि मैं इससे excel कर जाऊं, मैं इसको नीचा दिखा दूं. It shouldn't be like this. Future के leaders, I am talking to the future leaders. मुस्तकबिल के कायद आप बैठे हुए हैं. आपके ऊपर बहुत lot of responsibility rests on your shoulders. One thing which I am observing for the last half hour is that these professors, these faculty members, these students are gentle souls. Badi sharif ye, badi sharif. They are different from businessmen. They are different from bureaucrats. They are different from chairmen. They are very pious souls. And I am iska kail hu main. Dr. Qasim is sitting here, or isi tarah, there will be many people who are children of teachers. Teachers are so pure that they don't know the boundaries. There is no boundary. There is no Wagah border. There is no border between Pakistan and England and Germany and China where visa is required. It is the scientific community which knows no bounds. They don't require visa. So you are very brilliant people. Now coming lastly to your theme of this scientific college, I had been involved with my organizers, the technical faculty, technical organizers. Technical organizers must be looking at the CV, a curriculum vitae of all applicants very minutely to make their aptitude, their field commensurate with the theme. They must be doing like this. And your hard work has been forwarded to me by a couple of my seniors who used to be your part in the last 2 weeks. And they have said, and this credit goes to you and the faculty. I was told by one of my seniors who joined Pakistan Atomic Energy at the time when I was not born. Professor Dr. Tarak Suleja used to be among you. Okay. Yesterday, he apologized for not attending this ceremony on account of his family and very demanding masrufiyon unki wajah se wo nahi aaye. He said that I have a couple of things for you, Chairman, to convey on behalf of Atomic Energy Commission, that the faculty was very much brilliant. So I salute the faculty members. The participants were very relevant. One thing. Second, they were very attentive. They were not sleeping at the rear. Thirdly, they were inquiry mind. They agitated their mind as well, and that of the teacher who is studying and delivering. So this is very, very satisfying for me. This is what was desired. And we all know that we had been working on the this Nathia Gali Summer College for the last 6 to 9 months. And our dividend, which we were of the view that we should have those people who will take Pakistan in the fields of quantum technologies. I'm not talking of quantum mechanics. Let everything should be put into tangible things for the service of mankind. Let what you say that after 20 years, this generation will be, you people will say, those who are living in cave age, their gadgets, their computers, their mobiles were very slow as compared to now what we are having in 2040 or 2050. So we strive hard for making this dream a success, a reality. So it is very important that we should work upon quantum technologies wholeheartedly and with full pace while joining hands all over globe. I think, if I am not wrong, with my little knowledge, China excels in this field on globe. Everybody is lagging behind. I had been talking to Professor Dr. Manzoor, cryptography, what was that? It was from China to Austria, the entanglement, blah, blah, this. So they excelled it and they put a lot of money into that. And then came USA and Europe. So we should join hand. We are fortunate to have these brilliant brains. Instead of, मैं उर्दू में बात करता हूँ कि पेपर छापने के अलावा ये आपका टारगेट नहीं होना चाहिए. The brilliant professors all around the world are having only 8 or 10 worth papers, and they reach the age of 60 or 70. They are not having 200 papers at the age of 35 or 40. This should not be the target. It is just byproduct. Let the delivery should be there. तो मेरा आपको मैसेज ये है, हमें ये सिखाया गया था कि पेपर छापने हैं, मेरे में आपको तो नहीं सिखाया गया। वो बेटी जो ग्रीन बैठी हुई है वो पीछे हंसी है कि शायद आज भी ये सिखाया जाता होगा कि वी हैव टू एक्सेल। वो जो जमीला है वो साबरा से आगे उस वक्त निकलेगी जब all right, all right, all right. HEC, what HEC do? They require papers. They require papers. Good, 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 good. Chale, chale. This is one thing. When you will up दूसरी तरफ से plagiarism पे आप bound है ना, हम नहीं होते थे। मेरा आधा thesis जो है ना वो plagiarism पे, अगर मैं 94 का लूं, अगर मैं Manchester University, I graduated from Manchester University back in 1994. If I put that into that machine which tells it is plagiated, I will straight away be rejected. I will be put behind the bars. My all honors will be striped off. My thesis will be taken back. My title will be taken back. So the thing is, it's good. When the carrot will be shown to you to produce the papers, among those junk papers, 110 will come, I think, which will be deliverable. So it's no problem as long as when the sword of plagiarism is on your neck. So this is one thing, but the desirable thing is that you should be having those ideas which should be advancing your knowledge, science all over the globe, and putting service of science to the mankind. And this has been done. This has been done. What I have seen for the last 4 decades, this has been done. There used to be no bullet trains. There used to be no mobiles. There used to be no colored televisions in our childhood. There used to be no communications like this. These are fast computers like this. Mankind is going. And the semiconductor which you have studied this week, when we were students back in 86, the Silicon Technology Institute of Islamabad, Government of Pakistan, the Electronics Institute or Silicon, it was established at that time. And at that time, you will be fascinated to learn. I'm talking of 88, 86. In order to generate 1,000 megawatt electricity, at that time, there was no concept. We don't used to conceive what they are saying. Now you can conceive on account of the solar cells, on account of the solar energy, which you are putting on your roof and getting rid of WAPDA and something like that. At that time, those things were not there. In 86 and 88, our professor from UET Lahore said that if we want to get 1,000 megawatt from solar cells, those will be put in 85 square kilometer area. These photocells, 85 square kilometer area. If I simply say that it is 10 kilometer long this way, then 85 should be that. 8.5 should be like that. Now, and at that time, you will be surprised. अभी आप रो रहे हैं ना बिलों को, आपने बिल शिल जलाए हैं या नहीं? जलाने नहीं है यार, पे करने हैं, पे करने. At that time, it was not heavy on our pocket. 2 rupees, 3 rupees, 10 rupees used to be our bill. Although we were not having these ACs at that time. We were having these windows, open the windows, get the fresh air and get the fresh ideas as well. Fresh ideas. I hope you must be having fresh ideas, as told by Professor Walter, that this is the wonderful place where you can stand in this retreat hotel early this morning or early in the evening. Fresh breeze is blowing and you must have fresh ideas. against Robert Bruce, who was defeated again and again. And once he was standing, as I read that story in my childhood, he was standing and looking at these hills. And writer used to say, there was a fresh breeze, but no fresh idea. How to conquer, how to get rid of defeat on his enemy. But I know you must be having these fresh ideas. I am also a researcher, but I have left this 30 years ago. We were told that the best way is to get the ideas early in the morning across the riverside or the seaside, go to beach and have a walk, and you will be having fresh air and fresh ideas, and those your problems will be solved. I think I'm getting too long. The thing is, you must apply this, and next time, organizers, we will recollect what we gained out of these colleges. As I was discussing with you back in 70s, it was as novel, as novice as this quantum technology is there. And now we have matured, Atomic Energy Commission particular, have matured into tangible things which are being used on peaceful as well as non-peaceful purposes. So this is one dividend of this college, which I have witnessed, and I am witness to this. So I congratulate you for putting your efforts, whether you are sitting on the benches or the honorable faculty was putting efforts to inculcate whatsoever you can into your minds. So the faculty was wonderful, the students were wonderful, as far as the feedback of faculty and my other sources are concerned. And I am very thankful to technical as well as the or other administrative organizers of this esteemed college. And special thanks to our friends at the managers of this hotel. I am very much impressed, very much pleased, and I feel pleasure. And my support, the organization support of Atomic Energy is with this college. And I am very thankful to all these insignias. It is besides this, the Center for NCP. That's up. Thank you very much. Say to you and your DG. And the other is Pakistan Science Foundation. I think Dr. Beg has gone now. Who is the chairman now? Pay my special thanks to them. And then our old partner, ICTP. And then CERN, and then IAEA, and many others. And a special thanks to ICTP. This college is perhaps standing on the foundations of ICTP. Court decades have gone with this, we go hand in hand, and they are supportive on all things, technical and financial as well. So my special thanks to all these and all universities as well. When you go back, I think you will be having, apart from this, you have learned a lot from esteemed faculty members. You must have good relations now. This relationship is very important. This is another dividend which you are taking back. I was asking member science, are we on WhatsApp group? I don't know it is allowed or not, but if it is there, then you people will be excelling in relations and disseminating this knowledge in coming years. So thank you very much once again. I am honored. I feel honored and privileged. Thank you.
Thank you, sir, for your enlightening speech. Ladies and gentlemen, with this, we come to the conclusion of 49th International Nathia Ghali Summer College. I request all of the faculty members and participants to join the chief guest for a group photo outside. Thank you for your presence. Allah Hafiz.
Recording stopped. हासिल करदा डिग्रीज ACC अटेस्टेशन के लिए नाकाबिले